Yes, so welcome everyone to this new session of our Sapphire webinar. Today we have Professor Jason Nielsen to talk about the Inner Tracker Pixel Upgrade project for High Lumi LHC. So Professor Nielsen is a professor in the physics department, and he's the director of the Santa Cruz Institute for Particle Physics at the University of California in Santa Cruz. Before becoming professor at Santa Cruz, Professor Nielsen did his graduate work at the University of Wisconsin and his postdoctoral training at Lawrence Berkeley National Lab in California. He's active in measurements of the Higgs boson and also searches for new physics beyond the standard model with the ATLAS detector at the LHC, and he's also very active in physics studies and ATLAS detector development for the high luminosity LHC project, as already said. So in this area, he has made contributions to the readout electronics for the silicon pixel detector, development for simulation and reconstruction software, and studies of high energy WW boson scattering. So, Professor Nielsen, we are all yours. I will just stop sharing.
Well, thank you very much, Pedro, and thank you everyone for the invitation. I was very pleased to meet people from Sapphire at the recent Atlas Week in Vancouver, and I wanted to congratulate your institute for becoming a member of the ITK collaboration of the ITK project. So I'm looking forward to continue to work with people in your institute. So I wanted to give a seminar on the ITK ATLAS Pixel Project, but I also want to put some things in about what the project has looked like from a collaborator point of view and what the physics is that we're trying to achieve with this project. So I'll start by talking about what the motivation is for the upgrades. Move into the design of the ATLAS ITk Inner Tracker, which is an all-silicon detector, as you know. We'll talk about the development of the pixel detector components and some of the recent results that we have from prototypes and testing as we move towards the production of the detector itself. And then a few plans for the future and lessons learned in this project so far. I don't mind if people ask questions while the presentation is going. If you prefer to wait until the end, though, because it's your custom, that's okay with me. So I'll start by reminding everyone about the Large Hadron Collider Physics program. As I'm sure many of you know, the LHC program is a very broad program covering both proton-proton collisions and heavy ion collisions. Unfortunately, the PP running has ended this year for the LHC. We're moving on to the heavy ion collisions, still doing our part to take data for the heavy ion collisions, but I'm a little bit sad that we won't have as much luminosity for PP collisions as we had hoped in 2023. There certainly have been a lot of results that have come from the LHC, discovery of the Higgs boson, precision measurements of the top quark, both its production rate and its mass. I used to work on the top quark at the Tevatron, so I still follow all the top quark physics very carefully. And more recently, observations of vector boson scattering in many different channels, measuring many different properties, the couplings themselves, angular correlations that tell us something about WW scattering and ZZ scattering and how it relates to the Higgs sector. So these are getting very exciting. In general, I think the hallmark of the LHC program, and especially in Run 2, has been looking at measurements of very small cross-sections, that is, cross-sections that are on the order of picobarns or femtobarns. And measuring those cross-sections really requires a lot of data. It requires not only a lot of data, but ever greater precision in our Monte Carlo simulations, in our performance systematics, in our fit procedures. There are too many results to show, of course, but here's a recent result that I found very interesting. I hope you find it interesting too. This is a measurement of weak boson fusion production of VH. So it's a measurement of either WH or ZH, WH in this case. You can see from the diagrams here that there's an interference between two different diagrams. One that tells us something about the HZZ coupling and one that tells us something about the HWW coupling. Unlike most of the other cross-section measurements that all depend on the square of the sign of the coupling, the interference here allows us to get information about the absolute sign of the coupling. Well, the relative sign of the couplings between HZZ and WWH. It turns out, and this was a great thing for people to realize, that if there's a negative sign, that is, if the Higgs coupling to the Z and Higgs coupling to the W have opposite sign, then you get a huge constructive interference. You can see this in the plot at the top right. You can see that if we did have a negative sign, we have a huge increase in the signal cross-section for vector boson fusion of WH. And basically this analysis, even though it's not sensitive to the standard model production with the same sign coupling, is able to exclude the opposite sign coupling at something like 8 sigma. You see this in the plot at the bottom right. You see that the best fit is not the standard model prediction, but it's not excluding the standard model prediction. It's not measuring it particularly well, but it is very far away from this alternative prediction where you would have opposite sign. So I think that's very interesting. So this is just one of many results that were presented this summer. It shows that there still is a very strong LHC program measuring these cross sections that are very small. So ATLAS experiment to the LHC, instead of showing you the usual picture of the ATLAS experiment with the little person that's very small, I decided to show you an event display because our event display is so powerful that it actually gives you some good idea of what the ATLAS experiment looks like. So if you can zoom in your eyes at the right-hand side of this image here, you see the interaction point for the proton-proton collisions. And you see some blue and purple things in there. So what's blue in there is the tracker. And so you can see the tracker, the silicon part of the tracker. You can see the transition radiation tracker, the gas field tracker. And then you see that that's actually a very small part of ATLAS. You can also get some idea here about where the tracking ends in the current ATLAS detector. Especially the silicon tracking. So you can see that you don't see too many tracks that are very close to the beamline. And that would be one thing that we'd like to improve with the ATLAS experiment, to be able to measure tracks that are closer to the beamline with higher pseudorapidity. So we'll come back to that when we see the design of the ITK. Just a reminder of the current ATLAS pixel detector, because we'll be focusing on the ITK pixel detector today. We actually have two parts to the silicon pixel detector in ATLAS. We have what are originally called layers 0 through 2. Layer 0 is also called the B layer, which leads to a lot of confusion because now we have the insertable B layer. So when people talk about the B layer, they really mean layer 0. Insertable B layer, I don't know, it could be layer 00 or layer -1, but we just call it the insertable B layer. So there are 3 barrel layers here. There are a series of end cap disks that are used to make sure that the particles that are coming out are always remaining as perpendicular as possible to the surface of the detector. We prefer to have the particles going through a perpendicular normal to the surface of the detector because that minimizes the length of the pixel cluster. If you have a particle that's going through at a very oblique angle, you can have a cluster that's up to 18, 20 or more pixels long. And that makes it a little bit difficult, not only to disentangle the clusters that are formed by multiple tracks, but also to get some idea of the barycenter, the weighted center of that cluster. I found it interesting to think about what's the size of the silicon, what's the amount of silicon we have in the current pixel detector. It's about 1.8 square meters. And I think about the beach towel because here in Santa Cruz, we're on the beach in California. So relatively small amount of silicon when you think about it. How does this detector work? Well, this particular detector is what we would call the PNN detector. So you can see that we have a bulk of silicon that's N-type silicon. We have some doped implants that are N plus on the bottom and P plus on the top. And this P plus N junction is actually the reverse bias diode that we're using to deplete the silicon sensor of all the free charge carriers, so that when the charged particle comes through, for example, here from the top, it produces electron hole pairs, as said, about 20,000 electron hole pairs for every 250 microns of silicon. That turns out to be about 3 femtocoulombs. So that's the amount of charge that we're trying to detect in our preamplifiers and in our silicon readout chip. The IBL uses smaller pixels. The IBL has pixels that are 50 microns by 250 microns in area. It actually was built on the new beam pipe, and the new beam pipe and IBL were inserted, hence the name insertable B layer, into the current pixel detector. As we'll see, we're coming back to the idea for ITK about an insertable inner system. It's a little bit bigger than IBL, but the idea is kind of the same. You can see the IBL being inserted here at lower right into the pixel detector. The pixel detector performance has an interesting history. Of course, we're doing well with the B tagging and the flavor tagging and the tracking in the pixel detector. But really behind the scenes, this is due to some heroic efforts from retuning of the pixel thresholds and retuning of the bias voltage that's applied to those sensors. So the problem is that even the best sensors, which go in perfect on day one, eventually are subject to some radiation damage. And that radiation damage is in large part due to the proton collisions that we're studying. So it's the particles that we are studying with the detectors that are causing the radiation damage itself. You can see in the plots here that we tend to see a decrease in the charge collection efficiency over the years in the B layer, which is on the far right, and in the IBL, which is at the left. You might be surprised to see that the IBL is decreasing at a rate that is similar to the B layer, but in fact, the IBL sees more radiation than the B layer. You can see that the average fluence there in neutron equivalent per centimeter squared is about a factor of 2 greater for the IBL than even for the B layer. Now, we see that we have a decrease in the efficiency as the fluence increases, but you also see jumps up. And these jumps up come about whenever the detector is turned off so that it can be rejuvenated, or that technically some of this bulk damage can be annealed. And some of it can also be recovered by increasing the bias voltage. So if the bias voltage is increased, it provides a little bit extra energy for the electrons and holes that are trying to make it through the bulk, so they can overcome some of those trapping defects. This bias voltage has been increased every year. You can see it consistently increased during run 2, 2016, 2017, 2018. The other thing that you see here is you see these bands. The bands in gray and blue are our radiation damage simulation. And I would say really for the first time, we're able to model in a very precise way what the radiation damage is to the silicon detectors, put in the fluence and get some estimate of the charge trapping and therefore the efficiency. So we see that the IBL and the B layer are degrading over time. And that's one of the reasons that leads us to pursue the upgrade with the ITK. Of course, one of the big reasons is that we don't expect the LHC program to end anytime soon. Excuse me. We'll be moving on to the high luminosity LHC. The high luminosity LHC is necessitated by the replacement of the triplets. The inner triplets that are near the experiments are going to reach their radiation limit at the end of run 3. So we'll take advantage of that to launch the HL-LHC era, and ATLAS and CMS are both launching the upgrades, high luminosity upgrades. So from this schedule, you can see that the installation of those detectors will happen during long shutdown 3, and then you see that the LHC will run for run 4 and 5, integrating approximately a factor of 10 more than we'll have in run 3. There are many studies that were presented to the European Strategy for Particle Physics, the technical design reports from the experiments to the LHC Council. A lot of them focused on the physics opportunities. The physics opportunities include things like measurements of Higgs boson's properties, searches for beyond the standard model physics, the vector boson scattering that I had mentioned before and that I had done some work on myself. Flavor physics, including rare B decays with these very large luminosity samples. So a lot of physics opportunities that rely on the detector working at least as well as the Run 3 version that we have right now. It'd be nice to improve things, but certainly we would not like to have a detector whose capabilities are less than the detector we have now. Some of the concrete goals revolved around some concrete physics studies. For example, people noticed that the single lepton triggers in ATLAS are very important for the Higgs measurements, in particular WH measurement, where there's just a single lepton that's providing that trigger. The plot on the left is telling us that if we have to push up the muon trigger threshold for, let's say, 20 GeV up to 30 GeV, we get a significant loss in the acceptance for a variety of physics topics, including WH, including TT bar, perhaps most dramatically for some of the SUSY searches. So there's a very strong motivation to have a detector that measures the muon momentum precisely enough that we're able to include that information in the trigger and able to keep the same muon thresholds or as low as possible with a reasonable trigger rate. In the plot on the right, you see the effect of increasing the tracking information, extending it to a higher pseudo-rapidity beyond the 2.5 that we have now in Run 2, and increasing that tracking coverage out to eta of 4. We don't have the very last point on this plot. This is actually showing the track reconstruction efficiency for very highly boosted top quark jets, the kind of top quark jets that might be coming from a very high mass Z prime. But really, these top quark jets can be coming from just a regular TT bar production too, just happen to be very highly boosted. So this is an indication that we can do better for tracking and highly collimated jets with a new detector than we can now in Run 2. You see an improvement of efficiency of around 10% as we include that new detector. So these are some of the motivations. What we'd like to do is we'd like to develop a tracking detector that can maintain the precision on the muons, the precision on the tracks that are in the collimated jets, preferably out to high pseudo-rapidity. And so that's where the upgrade detector projects come in. I won't say too much about the other parts of the ATLAS upgrades, the calorimeter, the muons, the triggers. I'll focus obviously on the inner tracker replacement, the ITK. You can see in the plot at lower left here, the ITK layout as it was finalized includes tracking information out to an eta of 4.0. This is mostly made possible by the disks in the inner system, which I'll talk about in a moment. And you see in the plot on the right that the ITK does indeed have a better transverse momentum resolution than the inner detector by itself in Run 2, and even better than the combined Run 2 inner detector plus muon spectrometer. So the ITK by itself is much better than the inner detector that we have in Run 2. Okay, so we finally reached the ITK. What is the ITK? I think of the ITK as the inner tracker. I guess officially the name really is ITK. It's an all-silicon inner tracker that is no more gaseous tracker like we have now with the transition radiation detector. You remember that our beach towel-sized pixel detector had about 1.8 square meters of pixels. This has almost a factor of 10 more, 13 square meters. Add to that another 165 meters of silicon strip detector, and you see this is a very, very large volume to be instrumented with all silicon. Now we're thinking about a carpet sized of silicon pixels. The layout that you saw on the previous page gave you some idea that we have a very complicated structure with some parts that are flat. I'll go back for a second here. Some parts at low Z that are flat, some parts at high Z that are rings that are perpendicular to the beamline, and others in the intermediate region that are merely inclined. They're neither flat parallel to the beamline nor perpendicular to the beamline, but inclined so as to give us the best coverage at that intermediate pseudo-rapidity. One challenge has been to provide readout electronics that's radiation hard to the expected dose of 1 gigarad. Another challenge has been to provide a digital data bandwidth that is 1.28 gigahertz, eventually 10 gigahertz in the optical readout. And you can see that the preliminary results show us that the design that we have seems to achieve the requirements that we showed on the previous pages. We can see that the efficiency stays high for track efficiency from TT bar events all the way up to an eta of 4. It's not quite as high as in the center of the detector, but it's much higher than 0, let's put it that way. In the plot on the right, you see the effect of flavor tagging. Basically, what is the light jet rejection as a function of B-jet efficiency for different eta regions in the detector. And again, while the central coverage gives us the best flavor tagging, we get reasonable light jet rejection for a high B-jet efficiency, even for eta between 3 and 4, which we never had at all in run 2. So all these things are very exciting. To accomplish this, we actually have split up the ITK Pixel project into 3 subsystems. We have the outer barrel, the outer end cap, which is at high Z, and the inner system, which covers both low and high Z at small radii. Effectively, inner system is the replacement for what we called the IBL and the B layer before, similar radii for those two. So the pixel system will be inserted into the strip detector. The inner system will be inserted into the outer barrel and outer end cap first. So there's a staged installation that happens. The total in the entire pixel system is about 1.4 gigapixels. So it is one of the largest cameras in terms of pixels that we have of any instrument in the world. I was just thinking today, I think one of the telescopes in Chile is the other one that would approximate, would come close to the 1.4 gigapixels. That would be the Rubin Observatory, the LSST cam. Okay, and you see the breakdown by total pixel area there that I mentioned before. Now, if you want to see a different view for those inner tracker systems, the ITK, you can see the strip is also divided into barrel and end caps. You can see that the pixels are divided into effectively what you would have as a barrel section, perhaps with some inclined rings in the outer barrel, and then end cap sections that are essentially rings. You can see that the rings are mounted on cylindrical support structures. So you do see some structures that extend along Z. Those are the support structures. The detectors themselves are all in these ring structures. When we talk about the ITK pixel detectors, there's a series of components that are built together in order to form the ITK pixel detector. We start with the ITK Pix front-end chip, which is attached to a sensor, a silicon sensor that's sensitive to the charged particles. A flex module that's a flexible circuit that's mounted on top of the front-end chip and sensors. That is used to provide some surface mount components, but more importantly, to provide the interface to the bare module. Those modules are loaded onto local supports to provide what we call the load and local support. They are connected to power and data services, which are cables. Some are wire cables, some are flexible Kapton circuits. And then the data lines run out to the optical transceiver boards, which are located outside the ITK volume. The sensors themselves are interesting because we have followed up on the success of the 3D sensors in the IBL by defining sensors that are either planar sensors or what we call 3D sensors. So on the left, we have the planar sensors first. One important change is that ITK is moving to the N and P technology instead of the P and the N that was used in the previous pixel detector. That means that the substrate is a P-type substrate. The junction is still the PN junction that we have near the pixels. One thing that allows us to do with the N and P is to have all the processing on one side of the wafer. If you see this image on the far left, you see what would happen if we had a P and N or an N and N. We would have to have pixels on one side and then guard rings defining the bias voltage on the other side. The guard rings are there just to make sure that the edge doesn't have some high voltage across it, which would lead to some breakdown. So with this NNP processing, it's very convenient because we have all the implants, all the metallization on one side, with the exception of the contact on the back side that lets us connect the high voltage. So really everything is on one side. Those planar detectors have pixels that are 50 by 50 square microns everywhere. The wafer thicknesses varies. In some cases, they're 100 microns thick, in other places 150 microns thick. This is quite a bit thinner than what we have in the current pixel detector. So that means that we have a reduced charge collection, a reduced amount of charge, which makes the preamplification of the signal even more important. The other kind of sensor we have is the 3D structure. The big difference here is that the junction is given by a column that extends all the way through the bulk of the silicon. The idea here is that the columns are close enough together that the electrons and hole pairs don't have to drift as far as they would in a planar detector. So there are actually multiple columns per pixel as a way of making sure that the distance that those charge carriers travel is reduced. And in turn, this allows some of the trapping effects to be avoided, even when the radiation dose is very large. So the pixels for the 3D structures are either 25 by 100 or 50 by 50, depending on what part of the detector they're in. You'll notice that all of these come out to the same product, which is 2,500 square microns. And that corresponds to the cell size of the front end chip. That's not an accident that they're all the same. Before I move on to the front end chip, let me say a few words about how that was optimized. There were quite a bit of studies that were done to decide what parts of the detector would use 50 by 50 microns, what part would use 25 by 100 microns. So it was a trade-off between having the best transverse impact parameter resolution and having good longitudinal impact parameter resolution and resolving overlapping tracks. So in the plot on the left, you see the effect on the transverse impact parameter for single muons that have minimal multiple scattering, with a comparison between the clustering in 50 by 50 micron pixels and 25 by 100 micron pixels. So as expected, in this particular parameter, the 25 by 100 micron pixels do better because they're taking advantage of the improved resolution, the reduced pixel pitch in R5, which is needed for the D0 measurement. For the real comparison, maybe the best is to look at the flavor tagging. The flavor tagging takes into account the significance in the transverse plane and longitudinal to give you information, and you see that it's much better for the, well, there are some improvements for the 25 by 100 over the 50 by, I take it back. No, that is right. 25 by 100 has a better U-jet rejection for the same B-jet efficiency. All right, so I'll go through the different parts of the ITk Pixel project. We start with the front-end readout circuit. This was designed by the RD53 collaboration. It uses a 65 nanometer CMOS technology from TSMC. It's under test now for pre-production modules. The things are, it does have low power compared to what it might have been with all the digital circuitry and the powerful preamp. But it certainly is still a large contributor to the power, probably the largest contributor to the power draw of the ITk Pixel project. To go along with that new custom readout chip, we have custom data acquisition software, we call it YAR. The idea of YAR is new. It's an idea of using a host PC to do the operations for the data acquisition. Instead of having a digital signal processor or a core on an FPGA doing that work, the FPGA is acting just as a kind of an interface fabric, an I/O interface. And so it's taking the signals, passing the signals through the PCI Express bus onto the PC, and then the PC is doing the operations. So this is flexible because it doesn't draw too much on the processing power of the FPGA. By now, it's been ported to different FPGAs. And it seems to be working very well. It's a nice solution for all the labs to have a data acquisition system that's uniform. It is also a candidate for the DAQ software itself. So the Felix detector interface card has a similar sort of philosophy. It's a reconfigurable I/O interface. It's basically providing the fabric for the networking for the data acquisition. And there's no reason why YAR couldn't be the software on the Felix detector card, but that's still under discussion. One of the interesting points as we move towards more complex front-end chips and sensors is the joining together of the front-end chip to the sensor via bump bonding. And this plot from Sven Vassen is just fascinating. We see that the so-called standard flip chip bump that might be used in industry with a 150 to 200 micron pitch would simply not work for us because we have 50 by 50 pixel cells, right? So we need to go down in bump size. We end up being at the solder micro bump, which has the pitch around 20 or 30, up to 60 micron pitch, or even to the indium bump. So solder or indium bumps have a greatly reduced pitch compared to the standards that people have been using in previous years. This hybridization is challenging. We've engaged different industrial partners to work on the hybridization so that we have backups in case some have trouble, so that we can learn different techniques. And these lines seem to be going now. We can see when the bump bonds are not working correctly. We can measure the noise on the pixel and see that the extra capacitance from the chip or from the sensor is missing in some cases, meaning that the bumps are not present or disconnected. So it also can possibly be seen visually if the missing bumps are connected to some sort of aplanarity or bowing on the sensors, which seems to be the case with quite a few of these disconnected bumps. The module assembly itself depends on these flexible circuits that I mentioned before. And the sandwich always seemed a little bit upside down to me, but it's the hybrid circuit on the top, if you like, and then the sensor, and then the front-end chips on the very back. And the reason for that is if you see this exploded plot that's at the very far bottom right, is that the sensor and the flex are single units, whereas the 4 front-end chips that make up the so-called quad module are all separate and are bump bonded separately to the sensor. So the sensor and the flex are single units all the way around. So the flex can be mounted on that sensor, and these wire bonds come up off of the flex hybrid and down onto the front-end chips. So if we were to zoom in very far, we would see the wire bonds, and you see a little bit of them here in this module. Okay. This is an example of a triplet module that uses the inner system single chip modules. And this is an example of a quad module, which has 4 front-end chips attached to it. After the modules are assembled, they're sent to testing sites. We have distributed assembly sites and distributed testing sites around the world. The first thing that's done after the visual inspection is to do some electrical calibration scans. So each pixel is tuned, its threshold is tuned and noise measured to get some optimal operating parameter for each pixel. That is the threshold. And then the noise is measured after that tuning. Then there's a series of source scans that are done, scanning a source or multiple sources across the module so that we get some estimate of what's the response of the sensor to charged particles, to beta particles that are coming from a radioactive source. So this is an example, this drawing or graph at the lower part of the slide is an example of a complete stave with quad modules on it that has been imaged with a strontium-90 source. And you see that some of the corners of some of the sensors are disconnected. You see that one of them has no communication at all. And you see the shadows that come from surface-mounted components on the hybrid. And so all these are telling us about the response that we have of these modules to charged particles. Those modules are then mounted on local support structures. The local support structures are quite complex. They have to be thermomechanical units that are not only supporting in a very stiff and controlled way the modules, but are also performing well thermally. They're transmitting the power and the heat away from the front end chips into cooling pipes that are integrated as part of the support structure. So this structure on the left-hand side is what we call the longeron. It's part of the outer barrel for the ITk pixels. In this case, the modules are mounted on the bottom side of the longeron. They have little pigtails that connect on the side of the longeron, and then those pigtails are connected further to patch panel 0, PP0, that you see mounts on top of the longeron. So very complex mechanical structure. The thermal management has turned out to be quite a challenge because some exotic components are used in some of the thermal management. In particular, some aerospace foam. We've had quite a bit of competition getting that aerospace foam from suppliers. It's a very special foam. We think we have that procurement under control now, but it has been a challenge. I'll move on to the power delivery and the patch panels. So we mentioning energy out. We have to get energy in through power delivery. One of the things that's new for ITk is the use of serial powering. Instead of running a power cable to every module separately, we run a power cable on one side and then let the voltage drop across the first module and become the input to the next module. So this is a serial powering chain. It does require a large amount of current because you have to supply the current to all the chips and the modules all at once. So this leads to a very high current power line, and we'll see the consequences of that when we get to the connectors. So each one of these modules needs to have overcurrent protection, voltage regulator to make sure that the long serial powering chain is not providing the wrong voltage to any single module. Now, even though we are doing serial powering and reducing the material that's used for the power, nevertheless, the cables and the cooling pipes for pixels are still the dominant contribution to the material that scatters the particles inside. You can see this in the plot at the lower left, where pixel services and cooling seems to be the dominant contribution, even going all the way up to 8 out of 4. I mentioned the challenges of high power. One of the challenges of high power is finding connectors that can handle those high power and high voltage at the same time. It turns out that we have low voltage pins carrying 8 amps and high voltage pins carrying the bias voltage that can be up to 1200 volts in the same connector right next to each other. So this was quite a challenge to design this. We have an industrial partner that helped design a 58-pin connector with 1.5 millimeter pins for the power and 0.5 or 0.6 millimeter pins for the high voltage. Oh, and by the way, this connector is also carrying high-speed CAN bus communications for monitoring at 125 kilobits per second. So it's quite a complicated connector. We just got the first prototypes in hand this summer, in fact, during ATLAS Week. So we have been testing those in the lab. The connector that you see here with all its pins, each one of those corresponds to a tiny little black or gray plug on this patch panel. So you can see a huge number of cables coming out of the patch panel. The space is very tight at that patch panel. And one of the things that we continue to work on is modeling how the cables will be routed at PP1 to make the best use of that space. We have monitoring of the pixel services. I might go quickly through this MOP chip. It's a chip that has the same analog to digital converter as the RD53 front-end readout chip. It has the same voltage regulator. It has the same CMOS technology for radiation hardness. And the thing that's different is its communications bus is different. This is an ultra low power chip that can be turned on even when the power hungry front end chip is turned off. And so we can monitor the voltages in the chain even without the front end chip turned on. One of the big challenges has been getting all the data out. from the pixel detector. So the choice was made to move the optical transceivers outside of the ITK volume into a low radiation region. That means that the data signals have to be carried over copper links, electrical links, a distance of up to 6 meters before they reach the optical transceiver. So the challenge has been finding cables that can have acceptable losses, acceptable data losses over that long distance, and packing them into the very tight volume that we have in the detector. So to that end, we developed new high-speed twin axial data cables. So this is a differential line with 2 conductors. The key for keeping the losses low at high frequency is to keep the dimensions of the cable rigid, keep the impedance very tightly controlled and constant over the length of the cable. And this is achieved by having a rigid dielectric inside the cable. So you see in these 2 models of cable on the right-hand side that you have really a rigid, incompressible polyethylene dielectric that's surrounding both of the conductors. And in fact, they are completely locked in that matrix so that they can't move closer together or further apart, and therefore change the impedance. And the proof is in the test plot that we have at the bottom left here, where we see that whereas our requirement was to have a loss less than 20 decibels over 6 meters, we have a loss that is less than 1.5 decibels over 1 meter. So this cable loss of minus 1.48 decibels at the Nyquist frequency of 640 megahertz achieves the requirements by far. So this is a very successful collaboration with industry to develop these 2 cables. Even with those cables, the signal still doesn't look perfect when it comes out the other end. The signal looks like the plot that we have in the bottom left. You really can't see any differential signal at the output of this cable. It's there, but it's hidden behind the rise time, capacitance in the cable, jitter that's in the signal. So the GBCR chip, that is the gigabit cable receiver chip, has an equalizer built in to undo the cable frequency roll-off, the response of the cable to high frequency differential signals. And it also has a clock recovery part in the ASIC, so that clock data recovery, so that corrects for some of the clock jitter that you have going down the cable. So the same signal that comes out of the cable looking like nothing on the left-hand side is completely cleaned up by the GBCR chip, the combination of the equalizer and the clock recovery. So this is a big success too, and this eye looks fantastic, and the bit error rate is good after the GBCR. So I'd like to move from electrical now into the physical, mechanical, just to flash some slides of the installation mock-ups that have been happening for the different systems. Recently, SLAC was able to load rings and staves in the US with a tolerance of 75 microns. So this is a ring in the top right, a ring that is part of the inner system. It's a combination of triplets, that is single chip modules that you see in red in the inner radius, and quad modules that you see in green on the outer radius. On the picture in the bottom, we have a photo of a very long stave. This is a stave that's a single serial powering chain. So all those modules on that stave are powered by a single power line, which makes it very important for us to have robust power connectors for that single power line. Outer barrel has the demonstrator where it's a combination of the flat part of the barrel, you remember that from the ITK layout, and the inclined part. The inclined part of the modules are neither perpendicular to the plane nor parallel to the plane, but instead inclined. The real success of this demonstrator was that it's a full electrical system test, allowing us to check the entire serial powering chain, and perhaps equally important, to check what the grounding and shielding effects are from the carbon fiber support structure. We have to be careful not to induce any ground loops in this conductive structure and to produce extra noise for the ITK pixel detector. And then finally, the outer end cap also has its installation demonstrator. One thing to point out here is that the cables, instead of having cables, power cables, the power is delivered along this bus tape. It's a ring, it's a flat tape, very narrow. You can see it over here on the right-hand side where it says LV2. That's a trace from the bus tape. And you can see that it's connected to a little tab, a trapezoidal shaped tab, and then that power is delivered into the module itself through the so-called power tab. So very interesting design choices that are tailored to each part of the system here. Okay, where do these all go once they've been loaded? The SR1 integration facility at CERN is under development. And it has a large clean space for the installation of the detector, that is the insertion of the outer end caps onto the barrel and the inner system into the outer barrel, and then eventually into the strip detector. So this is very close to the ATLAS control room. If you've been to CERN, you may recognize the big building here on the right. The blue building right next to it is the SR1 building. So that's where this integration facility is located. You may ask where we are on the project schedule. It's very rough to write all this down where we are because different parts of the project are in different stages. The sensor design had been completed a long time ago. That is in production. The electrical services are still undergoing some prototyping and testing before entering in pre-production. But very roughly, I would say the R&D took place over a period of 8 to 10 years. The last few years have been used to produce prototypes and do all sorts of tests on them. We are now moving into the pre-production phase where we are exercising the production mechanisms and tests, expecting to move into production for most items in 2024, and then to move towards integration starting in late 2024 and 2025. That integration will continue through 2026 into 2027 when the ITK will be delivered to ATLAS at CERN. So I thought it might be interesting to give some personal view here. These are just my personal views on challenges and lessons learned so far. The hybridization, that is the bump bonding, certainly has been a challenge. You saw that we're pushing the limits of what that bump bonding can do. The module assembly procedures require a lot of precision and a lot of trial and error for some things, gluing and positioning, finding the things that work and sharing them with the colleagues around the world. Technical lessons. One thing that I learned personally is that the high-speed data bus design that is transmitting at gigahertz signals requires a set of new tools, not only design tools, but even laboratory tools, right? The megahertz scopes won't cut it anymore. You really need 10 gigahertz scopes in order to see what's happening with these signals. And I would say another technical lesson is that when you're trying to build new sensors like the 3D columnar electrode sensors to engage several different foundries, the challenge is significant, and having a bunch of options is a good thing to implement. In collaboration lessons, I found that defining the interfaces early is very important. With every team, every institute designing a different part of the experiment, it's all too easy to wait until it's too late to decide what connection is supposed to go where, or what line passes all the way from the module through the PP1 connector. The other thing is that anything is possible. It's always possible to find a solution to the problem. It just may cost you. It may be so complicated that there's only one supplier that can do it, and even it's a challenge for them, and so they will charge you a lot. So simple solutions are much preferred if possible. So what's next? This is the ITK Pixel project. We mentioned that it will be delivered to CERN in 2027 for insertion into ATLAS. The HLLEC program will start then in 2030, and actually I think it should start in 2029. if I remember right. Run 4, then a long shutdown, a 2-year shutdown before embarking on run 5. Some people are excited about the possibility of using long shutdown 4 to put in a new pixel detector that could replace the inner system layer 0 and 1. And this would be a chance to even improve the technology there. 2 plausible technologies that people are thinking about: the so-called monolithic active pixel sensors, which are integrated sensor and readout electronics into a single package, and the low gain avalanche detectors, which include not only good position resolution, but also time resolution on the order of 10 picoseconds, which can be very useful for suppressing pileup from collisions that happen at different times. And the last bullet is just a nod to the fact that we did R&D for the ITK for about 10 years, and looks like run 5, or the long shutdown 4, is only 10 years away. So we have only 10 years left to prepare the R&D and to complete the production if we do have a new system. So that'll bring me to my summary. I told you about how the ITK Pixel project stems from the stringent requirements for physics. I mentioned a few things that are new for the ITK Pixel detector that help me to meet that challenge: smaller pixel size, the serial powering, coverage at larger eta values, that is more forward to get more information in the physics. And the project is moving in its stages from prototype into pre-production for different parts of the project. I would say it's been an exciting project and a good learning experience for all collaborators, whether they have built pixel detectors before or whether they are students and young faculty building a pixel detector for the first time. So with that, I'll thank you for the invitation at the seminar, and I'm open to questions if people have any. Thank you.
Thank you, Jason, for such a complete and engaging talk. So now we have time for questions.
I have a question.
Yeah.
Yeah. Do you have any strategy for future? Let's suppose you will, during this pre-production and production, you will create very good team of people, young people, but then they will move to another institutions and everything will be changed. How to keep very good team around this super detector? Do you have a strategy?
Yeah, it's a good question. We also struggle with this at our institute. So one way is to become involved in whatever is coming next in long shutdown 4. That will not be a very large project. I mean, it won't be physically large project because it will be the inner system. But I think there are some opportunities there to bring in some new technologies and to be involved. I think the discussions haven't really started for that yet, but that is a natural outlet for people that are interested in building.
Is it in frame of RDs, new RDs of CERN?
New ideas or new R&Ds?
No, new RD, research and development programs of CERN. Is it in this program or not?
Those programs are supposed to be, as far as I understand, independent of the experiments. They're really supposed to be R&D into what is needed for the next generation of colliders, for example. Maybe another way to put it is, I'm not sure that they will have R&D concepts. No, I guess they will. They will happen over the next 10 years. So there is a chance that some of that work could become. I think that what really supports the institutes, though, is project. I think the R&D program at CERN is useful in terms of developing new ideas and developing prototypes, but there's nothing like an actual project to get people excited about building something at large scale. That's the thing, is that we tend to do R&D projects on individual pieces, an individual sensor, an individual readout chip, an individual module. There's never a call for building something big until you build something big. And so one of the R&D projects that people are trying to promote at CERN is the large scale integrated structures. In other words, how do you produce a module assembly in an effective way at a large scale? How do you do testing at large scale? So Sergey, you're right. I think that the R&D programs at CERN will be the natural place for people who are interested in pushing new ideas. I hope that people will contribute to the operation also of the experiment at CERN, because this experiment, or this detector, the pixel detector, the outer parts of the pixel detector, will be there until 2040, 2041. And everything that people are learning in the lab about how to operate these modules will apply at CERN in the cavern. So I also hope that's a way for people to learn and use their expertise about the silicon detectors. Okay,
but last question.
Yes.
Now, if you consider, let's say, ATLAS RD or ATLAS ITk RD, does it mean that it will be just ATLAS RD, or it will be RD of all LHC detectors, or ATLAS and CMS RD?
Well, that's a good question. I had the impression that these R&D programs were set up to be somewhat generic. You may think back to RD50, for example. RD50 was a successful collaboration at CERN that developed sensors for many different projects, mostly aimed towards the LHC, but in principle, general enough that they could be used in many different places. RD53 is a collaboration that ends up producing the front-end chips for ATLAS and CMS, even though it may have been started as a way to explore new technologies. So I believe that those R&D programs at CERN are intended to be generic enough that they're not limited to ATLAS and CMS, which means that I think there would have to be another layer between those R&D projects and the experiments to bring in the ideas from those R&D projects to the experiments as concrete projects. So I hope that answered that question. And I have to confess, so far I have not seen that such a layer exists in either ATLAS or CMS. But then again, I haven't seen that the R&D programs exist yet either.
Thank you for your question and for your answer as well. Do we have more questions?
Maybe I have a question. Hi. No, just your opinion. After ITK is installed, etc., where are you moving in terms of these new technologies, new detectors?
So our institute is very interested in these timing detectors, the so-called LGADs. And we're interested in the LGADs not only for LHC, but also for other experiments like the electron-ion collider, like some fixed target experiments that could look at pion decay. The Pioneer experiment, for example, proposed this sort of target. And especially designing time resolution, time-sensitive sensors that can withstand high radiation doses. You may know, for example, that the LGADs are built on a very carefully implanted layer in the silicon. And if that gets damaged or the diffusion happens as a result of radiation, you can lose the properties of the good time resolution. So people are looking at ways to try to maintain that even with large radiation dose. I'm also personally excited about the maps, but the maps are very challenging. And you can imagine, I think you know how challenging it is to do CMOS design in any case, and to do something where it's CMOS design while still maintaining the properties of the sensor. I think that's extremely challenging. It's interesting, but it takes a lot of resources to participate. And I think that might be a barrier for some institutes being able to participate. Maybe one way to go about it is to be involved in the testing of those maps, right? And be able to do careful characterization. Maybe that's a different set of skills than actually doing the ASIC design.
Thank you.
And I have to confess, I'm really excited about operations too for LHC. After having worked in the lab for all these years, it would be very interesting to get this detector into the cavern and actually see it taking data and be in the control room.
Any further question? I do have one question though. When talking about 3D sensors, so when you were explaining the planar sensors, you said that it was crucial, or it was very important that the particle passing through was most perpendicular to the sensor. With 3D sensors, this is not so important.
It's interesting. It's still technically perpendicular to the sensor itself, just not to the electrode inside the sensor. So the whole point there, why do we want it to be normal to the sensor? What we're trying to avoid is we're trying to avoid a particle passing underneath many readout pixels, right? And because then you just have a very, very long cluster. So in that case, what really matters is the aspect ratio of the trajectory of the particle. Is it going through at a very shallow angle to the wafer, to the silicon wafer, or is it normal to the wafer? It almost doesn't matter where the electrodes are in that particular case, because the readout still happens on the pads, the pixel pads that are on the surface of the detector.
I see.
I guess another way to say it, Pedro, is we don't have readout pads throughout the column and the bulk. It's only at the top of the column.
Yes. Thank you. So if we don't have any more questions, I would like to thank Jason again, and we will meet next month, I guess. So thank you everybody for joining and participating. See you later. Thanks again, Jason.
Thanks.
Bye. Have a nice weekend.
Thanks. Bye.